Thank you very much. What I'm going to look at today is a little change in focus from what you currently heard. When we talk about big data, we're going to look at big data through the lens of complex systems, because any clinical setting that you deal with is indeed a complex system. So a couple things that I want to go through here, and I have a lot to go through. Hopefully I'll be able to fit it in the half-hour limit. But I wanted to sort of acquaint you with sort of system science and how it intersects with big data and why it is an important area. So we talk a little bit about big data and complex system science, what's new and what's different. The idea of complexity in information, how much information is enough when you're dealing with large complex systems. Searching for common system behaviors is going to be very important, because that really begs the question, how much data or how much information is enough to basically close the system so that you understand something about that system as a whole? How much information is really required to do that? What are some of the indicators of system change that we use in the complex sciences community that could be literally mined for this big data application? And what's important in all of this is at the end, you have to ask yourself, okay, how much risk is involved when you assess a patient in a clinical setting and you're using predictive indicators? What kind of risk is involved in this, and how do you manage that risk? So there's a risk assessment and a risk management component to this. And then I want to talk a little bit about possibly a notional framework that pulls all this together, that pulls some of the lessons learned from complexity science and some of the lessons learned in modern risk assessment and risk management. So the good news here, though, and I'll emphasize this over and over again, is that there are analytic tools that are available within the complex science community that can help you today, and they can be shared. Okay, not only MITRE has developed a lot of these tools, but a lot of other folks have as well. And those tools are available for use within a clinical setting. So that's going to be sort of a common theme throughout this. The fact that we're almost maniacal about shared analytics and the importance of shared analytics. Okay, when you talk about big data characteristics, you probably have seen a chart similar to this before. And this is really just to set the context. Big data really focuses on collecting as much information as possible. And there are four components to this. One is volume. When you look at things in a clinical setting, you're dealing literally today with exabytes of information. Within a decade, you're going to have zettabytes of information. 80% of that data is really derived from imagery information. The second important thing is the velocity of the data. You don't want latency in the system, so you're going for real-time data flows, okay, which really means you're looking at distributed types of systems like MapReduce, Hadoop, whatever, that allows you to chew on data very quickly so that you can get data out in a relatively short period of time with minimal latency. There's variety, which is you're really dealing with heterogeneous data sets, whether you're dealing with structured or unstructured electronic patient records, for example, genomic information, clinical information, behavior information. It could be one-dimensional data, two-dimensional data, three-dimensional data when you're dealing with imagery and above. It's the variety of information that's important. And the fourth important thing is the veracity of the information. Data assurance, hardware and software, and distributed architectures. So the focus on big data, again, is collecting as much information as possible. Complex systems has a slightly different perspective to the problem. That focuses on collecting only information that's relevant to determining what's important and what's not. So what does this mean, really, in this four-axis setting of volume, velocity, variety, and veracity? Well, before we do that, let me just sort of set a little context on what really is meant by a complex system, because it's a very broad set of terms, and you probably have seen a lot of this in the literature already. The formal definition is it's really a network of interconnected, heterogeneous components that interact in a nonlinear way. And if you look at different things like climate, for example, the climate is a very nonlinear, highly connected process where the atmosphere is connected to the ocean circulation patterns, so on and so forth. Ant colonies, for example, where you have collective emergent behavior there, is another example of complex systems, and you can go all the way down. What's interesting is MITRE has spent a lot of time, and this is sort of in an interesting area, looking at the bulk electric power grid. And one of the things that you learn very quickly about the power grid is it's a coupled system with unintended consequences. What does that mean? Well, we've worked with FERC for 3 years now, which is the Federal Energy Regulatory Commission, and they were very concerned about how their decisions actually impacted the bulk power grid. And we looked at the East Coast interconnect along the East Coast. And the remarkable thing about a complex system is the unintended consequences. If you have a blackout in a given area, common wisdom sort of says that you're going to get another blackout in that area of equal or lesser severity. It turns out not to be the case. If you fix one problem where a blackout occurred, you can have another set of cascading blackouts occurring hundreds of miles away at various levels of intensity. Okay, so from a risk assessment, risk management point of view, this becomes very important. Think about in a clinical setting now, where you look at your predictive indicators, your big data indicators, and you ask yourself, okay, the clues that I'm getting in terms of what's happening, how does that really affect the overall system? Okay, what is going to be the impact of the decision I make on the overall system? When you ask that kind of question, you're really dealing with complex systems, and it's a very difficult kind of problem because, as you're probably aware, features of complex systems are you do get these cascading failures. You got really many local interconnections, and you can produce emergent behavior in the sense that the whole is really greater than its sum of its parts. Okay, you can get interesting patterns coming out that you never really expected before, but isn't that really a complex biological system anyway? So the big question then that it really begs in all of this is what can you do about this? Well, when you represent a complex system, there's what's called complexity, and it's called Weaver complexity here, but there are 3 types of problems. The first problem is a very simple problem where if you can write down a mathematical expression for this and you can model the system from beginning to end and you understand the cause and effect relationships, then that model is very simple. In this picture I have here, it's a very simple physics problem where you're asked to calculate the terminal velocity of a block sliding down a frictionless plane, okay? Well, there are different ways, obviously, right, that you can solve this problem. You can go in and you can actually look at the individual atoms that make up the block in the inclined plane. You can do all the averaging. It'd take you 2-3 days to average everything up on a computer, and the end result would be, guess what? You would get Newton's laws back again that basically prescribe what the terminal velocity is. You don't have to do that. And that's what insight buys you in the sense, is that you know if the problem is simple enough, then you could ignore actual behavior that's occurring on the finer scales, okay? Another way of having complexity is what's called disorganized complexity. Think about this as a gas, for example, that's moving around in a container, and you're interested in looking at certain macroscopic details of that gas, okay? Well, the gas molecules themselves are almost highly uncorrelated, so you're dealing with almost an independent set of components. But there are theories that have been developed in the complex science community to deal with those things, and are called mean field theories. I think more relevant to the problem that we're looking at is organized complexity, where you look at this as a bunch of embedded Russian dolls, where one component actually fits within another component, you have complexity that grows on a spatial and temporal scale, and there are ways of dealing with problems such as this as well, and that's called the use of agent-based models. So the important thing here is that the type of complexity that you're dealing with really determines the type and the amount of information that's required. And what I like to look at is what's really called the complexity profile, where you look at the scale of a system that you're looking at. It could be a biological system, it could be a man-made system, but you look at its parts at different scales. And you ask yourself, what's the required amount of information to actually understand that part of the system? And not too surprisingly, what you find is that the finer the scale you're looking at, the more information is required to understand that, because you're looking at all the details of the system. As you're going to coarser scales to the right along the axis, so you're looking at large scale behavior, it really requires lesser information. It turns out that when you're dealing with complex systems, whether they're man-made systems, whether they're biological systems, doesn't matter, the most important region is really at the higher scales, or the coarser scales. And you may ask, why is that true? And the answer really is because it's at the coarser scales where a human is interacting with that system. That's what you're actually seeing. You're not seeing the fine scale independent components, you're seeing the more coarse-grained kinds of components. So that's really the important region you're looking at. And again, I bring back this thought experiment of the inclined plane problem of how much information is required to actually solve the problem. It turns out, not too surprisingly, it depends on the question that you ask, okay? If your question is fairly simple, which is a basic freshman physics problem of what the terminal velocity is of a block sliding down an inclined plane, then you don't have to go through the fuss and bother of looking at this problem at a very fine scale, because you don't care what's happening at the atomic or molecular level. You're more interested in what's happening at the macroscopic level. If you are interested in the finer components, then you can slide off. But mostly for our kinds of problems, we're interested mostly in the coarser grained scales. So again, the most important information about a system for informing action on a system is the behavior of that system at the largest scales. Okay, so if we're interested in focusing on the coarser scales, then how do we get to that point in a complex system? Here's where the beauty of the problem comes in, because there's been a lot of work throughout the community looking at what are universal properties of large systems when they undergo profound changes in state. It could be a change in state for a cardiac patient. It could be change in state for a man-made system. When it undergoes a state change or a phase change, you can exploit that behavior, and all systems begin to look alike in a sense that when they undergo that kind of phase transition, that special kind of phase transition, you can actually mine that behavior using data analytics and apply it to your problem. So a system can have the same behaviors even though they differ in the details. And the examples are, if you look at, say, water, a liquid, from a freezing state going to a liquid state, which is a non-isotropic condition, both in the freezing and non-isotropic condition, there's really not much of interest going on. What happens is that all the interacting dynamics occur as you go from the freezing state to the liquid state to the gaseous state. And really, if you think about it, that's really where we want our data analytic tools to apply. We really want to apply them to those kinds of cases where a system is undergoing a change, because excuse me, that's what we want to look at, particularly when we start looking at risk assessment and risk management. Fluid flow is another problem, from a laminar state, a very gradual flow, to a turbulent state. And it's true even when you deal with distributed systems. This diagram on the right could be a social networking diagram of people interacting with other people on Facebook or Twitter or whatever. And depending upon events that are occurring outside, this whole system can become reorganized very quickly. So it's that transition from one set of dynamics or one set of interactions to another set of interactions, which is really what's important to the problem. So I claim that the only description that's really important is the one that has universality. That is, descriptions are not dependent on particular outcomes, okay? So that you can have different kinds of biological systems, for example, or different behaviors in a clinical setting that on the face of it look quite different. But as those systems undergo change, they take on properties that sort of mirror other like systems as well. And that's really what's called universality. And that's what's really important, I think, personally, when you start developing data analytic tools, because you really want to exploit that kind of phenomena. So very quickly, some of the descriptors of universality, and there are many, and I'm not going to go through all of this, are things that we actually developed at MITRE for various problems other than just in a clinical or medical setting, but they work very well. And one of the very interesting things, which is a very simple predictive analytic metric to look at, is what's called critical slowing down. This actually came out of the biological literature. This was an article that appeared about 5-6 years ago in Nature magazine by Stanley and his workers. He found something very interesting about biological systems. As they undergo certain phase transition, the behavior of those systems near those special critical points or phase transition points, he found that the recovery rate of that system actually slowed down. So a very simple way of looking at this thing, and it not only applies to biological systems, but a lot of other things, is to look at sort of a landscape function where you're rolling a ball sort of down into a valley, okay? If that valley is very steep, that ball will roll down into that valley very quickly and sort of be locked into that state, which is shown in that diagram to the left there. So if you start rattling that system, you're not going to get really much interaction. That ball is really going to stay in that valley and everything is going to be very stable. We say that that's a resilient biological system or a resilient man-made system. As you go through a phase transition, you're actually taking that landscape, and it's almost like a rubber sheet that you're pulling on, in a sense, is that you're flattening that valley out now. So there's less of a distinction between a hill and a valley. Now that ball is rolling down, but it rolls down much more slowly. And at the same time, what's in that valley, which is very shallow, if I start rattling that system, I'm going to see a lot of fluctuation occurring in that system, okay? So a telltale sign of critical slowing down is that your statistical variance, or the degree of fluctuation that you see either in a biological system or a man-made system, increases. Guess what? That applies to a lot of different systems. We've actually developed tools that allow you to exploit that, and they are shared analytic tools that are open to all of you in this room to use, okay? But they're very general tools in a sense. Notice that we're not applying this to a particular type of biological system or a particular complex system. These are universal or general properties of large complex systems when they undergo novel changes in behavior. And these are tools that you can use to exploit that. Another interesting thing is what's called percolation. And percolation is the sudden onset of system-level behavior where all the components of a system become connected. And this is very interesting because it has a lot of ramifications in terms of the spread of, say, forest fires. Depending upon how many trees that you have in a forest that are dried out due to lack of rain, okay, you can predict, or you would think that you could predict, that as you had more dry trees in the forest, you would have a gradual increase in the fire danger within a given area. It turns out that's not the case at all. It turns out there's not much change occurring until a sudden onset event occurs where you have enough dry trees in that forest to actually cause the entire forest to start burning. And that onset of behavior is what's called percolation. I like to use this analogy of an old style, and if you're as old as I am, you probably know what this is. This is an old style percolator where you have water in the bottom and you have coffee grounds in the top. And what you do is you heat the coffee. You have to wait interminably long. It's not like modern day coffee makers. It takes 15 minutes, but there's some zen attached to actually watching this happen. But so as the water begins to actually propagate up because you're increasing the pressure in here, it begins to saturate some of the grounds. But if you notice carefully, and maybe if you're as crazy as I am, because my background is in physics, you sort of get off on looking at things like this. But you find out that you don't get a sudden onset of all the grounds in the upper container being saturated immediately. You get some grains that are saturated, some other grains that are saturated, but almost instantaneously you find that all of a sudden the top of the container starts bubbling. And what's actually happened there is that now the water has permeated all the grains. The grains are acting as a collective complex system. They're coupled, which means there's a long-range spatial correlation within the grounds in the upper chamber. And that's what causes the onset of this rapid boiling in the upper chamber. That's what's called percolation. Again, it occurs not only in physical systems, it can occur in biological systems, any other kind of system that you're looking at, provided you have that set of connectivity. I'm not going to spend too much time talking about scale and variance other than to say that that's another important hallmark of a complex system, is that you have certain scaling laws that come up. Like, for example, you look at the predominance of earthquake activity of a certain magnitude, and you ask yourself, okay, what's the probability that I'm going to get an earthquake of this given magnitude over this period of time? And you find out it really satisfies certain kinds of scaling laws. That really gets into the amount of information available. Another measure of that is what's called entropy. And both Randall Moorman and his co-workers, Doug Lake and others, have actually exploited some of this scale invariant behavior in developing what's called sample entropy predictive analytic tools that can be used for this purpose. And again, that's a shared analytic tool that can be used throughout the community. And the last one is criticality. And criticality I talked about a little bit in the fact that you have competing processes that occur as you go through these phase transitions. And they're beautiful tools that you can use from the community to actually determine when you're going to get that phase kind of transition occurring. And you can actually measure when those phase transitions occur. And that's what's called, and I'm not going to get into the detail, multifractal processes. All it really is that you're looking at an interweaving of a number of different processes that are occurring at different temporal and spatial scales within a complex system, and they're all interlaced. The question is, how do you measure that kind of interlacing? Well, guess what? Again, we've developed predictive data analytic tools that actually allow you to go in, measure that, and then make predictions about when a system is going to undergo a critical phase transition. Okay, so data analytic tools have been developed for these descriptors. There are a number of them. There are also parametric models, which I'm not going to spend too much time on. I think I mentioned mean field theory, which is basically a way of dealing with disorganized complexity, where you don't have this nesting, where you have basically components that are sort of independent of each other, but they still act as a complex system, and you want to ask yourself, okay, what's the average performance of a system such as that? And there's a lot, again, that we had developed at MITRE based upon physics-based models that allow you to take a very intractable mathematics problem, because you're looking at large number of objects, and you're breaking it down into a simple enough form where you can develop sort of mean estimates of what that system is doing over time in space. We've applied it to a lot of radar communication problems, which is very interesting. In this case, you have, say, hundreds of radars and hundreds of communication systems, think of cell phones, competing for the same spectrum or the same bandwidth. Well, what's the performance of the radars and communications in an environment like that? Well, on the face of it, it's an intractable problem unless you look at large numbers, okay? Large numbers of radars, large number of comm systems, and you find when you do that, the problem actually condenses down to something much more understandable. And I think the end goal, at least from my perspective in developing these data analytic models, is just not, it's not sufficient just to say that I've been able to sort of measure or quantify what's going on. It's also to understand why those metrics are saying what they're saying. What is the functional relationships physically that tie those properties of a system together? And I think that's as important as actually performing the measurements themselves. The other point is the use of agent-based models, and we do a lot of work in agent-based modeling. But what we do is we add a little of our own secret sauce to this by adding meta-models to this that actually understand what the functional relationships are between the input and output of these models, so we can build very parsimonious models to understand what the functional relationships should be. And for a lot of problems that we do across Department of Defense, DHS, Homeland Security, and other areas, these methods work very well because they allow for a very succinct representation to a problem that's almost intractable if you look at all the data that's really produced out of an agent-based model. So it's a way of basically codifying and sort of reducing that kind of stuff down. Okay, well, all of this stuff really wouldn't make much sense if we couldn't somehow tie it into this notion of risk assessment and risk management. And I only have a couple more slides, I promise. So the way we sort of look at the problem of risk assessment and management is, first of all, you have to actually start thinking about what these complexity-based indicators are. These are your data analytics applied to complex systems. And remember, the holy grail here is to exploit novel transitions or changes in complex system behaviors that can occur. And that's really this whole area of what we call universality. And that really helps us in developing our data analytic tools. But once we have that, we then have to understand, okay, how do your decisions affect outcomes in a complex nonlinear system? So we actually go back and develop fault and event tree analysis to understand, okay, what parts of a system are more resilient than other parts? What parts are more prone to problems than others? It could be the bulk power grid system, it could be anything else. But based on that, we can then develop a vulnerability and risk analysis on that by saying, okay, if these things happen in this particular order for this particular system, then we can assess the probability of a vulnerability occurring. And we can also start developing risk mitigations and optimal resource allocation strategies to overcome those. So from a complexity-based indicator point of view, we use both parametric and non-parametric data analytic approaches. Some of these I had already discussed. They involve mean field theories, agent-based models, critical slowing down, percolation, scale invariance, criticality. The list goes on and on, but these are the highest, at least in our priority. And in the data analytics work, we're interested in actually developing a knowledge repository. Part of the problem is that since we work broadly across really different types of problems and the application of complex systems, it's important to develop a knowledge repository where we can begin to share analytics. So from a MITRE standpoint, we're already doing this in terms of having a database of tools that our engineers can draw on. And the hope is by thinking about data analytics and big data from a complex system perspective, we can start thinking about the use of shared analytic tools that have been developed within the complexity community that could really help you folks in this room actually solve your problems. So if you start putting the pieces together, this is something that we had been thinking about, is that when you look at really designing a clinical decision support toolbox, I think there are important components to all of this. Okay, there are self-training tools that allow a novice to go in to understand how to apply the tools to solve a particular problem. User guidance management services. The last two are incredibly important, I think, in our mind, is the sharing of analytics. Having a capability directory set up that people can pull on, where people can actually trust, basically, the shared analytic tools that are in there. So there's a vetting approach that goes on before those tools are ever included within the toolbox, and a knowledge repository. And we look at this as really being composed of four components: the data discovery and validation, the data aggregation transformation. I think the important part from our standpoint here is really the modeling, SIM, and data services point, which really should be the focus of our work. And that really involves the development of the data analytics tools, the decision support tools, the risk analysis tools, and a way to basically assess the various scenarios. And when we're dealing with this, outcomes and feedbacks, we have to develop metrics and indicators of performance that sort of rate the quality of the data analytic tools that we use. And that assessment across the community should be open so everyone can sort of see the applicability of using these tools for certain applications, because not all tools can be used uniformly across all sets of problems. And the question is, what are the assumptions that are involved in doing this, number one? And secondly, once you know what those assumptions are, then how valid is your application of that tool to your particular type of problem? So really, that's the end of my presentation. I know it was a whirlwind tour, but I wanted to at least get you acquainted with the fact that when you talk about data analytics, it's much broader than we ever thought, because there actually has been a lot of work being done in complementary communities outside the medical setting, and that's the whole world of complex system science. So there are a lot of different tools and methods that can be shared that could help you today. So, we can talk offline and engage in conversation tonight about this, but there are a lot of interesting things that could be done above and beyond the traditional kinds of tools that people are thinking about. Thank you.